today, we do not want to get any new C++ users. We hope that you will all use Java or Kotlin if you can. But obviously, there are people who can't, and we're here for you. And so I think what we really want to say is just we are working on C and C++. We do care. We're trying to make things better. And we want to talk about some of the things that we've been doing over the past few years. So specifically, we are the platform, the OS C++ team. And we took over the NDK around 2015 for R10. The parts that we consider the NDK are basically the compiler, the headers, and the libraries. So we're not talking about things like the Studio integration, the Gradle stuff. The Studio folks are around. They've got numerous talks, and you can talk to them other times. So Dan's going to start with a introduction to what we've done since we took over the NDK.
Yes, so like Elliott said, we took over in about May 2015. That was NDK R10E at the time. So I'm going to be covering from then on. To give some perspective, what the OS C++ experience looked like back then, this was Marshmallow. We were most of the way done with that. We had the transition to Clang well underway at that point. We'd moved a device in its entirety. We were working on others. We had complete C++ 14 support from libc++ at that point. Google is big on dogfooding, so the idea being, we should be using what you're using so that we find the bugs before we ship them to you. Unfortunately for the NDK at the time, this is what things looked like. We had 4 different compilers. That was 2 versions of GCC, 2 versions of Clang. Clang was heavily forked. 3 different C++ libraries. We had STL port, hadn't received updates upstream in years, so it was still on C++ 03. We had GNU STL, more commonly known as GNU's libstd C++. That's what you have on your normal Linux system. And libc++, which is LLVM's C++ standard library, which we're using in the platform. This was also quite heavily forked in the NDK, and it had a compatibility library that let it run going back to Gingerbread, and that library had quite a few bugs, unfortunately, so that was a major source of issues. We also had a copy of the OS headers for every single API level and architecture, and typically that meant that if we fixed a bug in the headers, we only fixed it in the most recent version, and it didn't get backported, which was a big problem because you were using whichever version of the headers matched your min SDK version. So if we only fixed the latest version, you wouldn't actually see the fix for about 5 years, maybe more. So the question is, how do we get to this dogfooding world? And we could essentially either just stop shipping NDKs for a couple of years while we dealt with all of the issues that had to get us there. That didn't sound particularly appealing, so instead we tried to do this in smaller, less disruptive steps. Each step still had some disruption, but it was a much easier hurdle to get over. We did this in a predictable opt-in, opt-out, and then remove cycle. If I use the unified headers as an example, R14, we added a flag to turn those on. R15, if your app wasn't ready to switch yet, you could still opt out with a different flag. And then by R16, we'd worked out all the kinks, and we were ready to move on, so we removed the previous option. The compilers, we started with this, really, with R11. That was when we unforked the NDK's Clang, and that alone let us close just a ton of bugs. It was then the same compiler that we used to build the OS. R13, a couple releases later, we switched that to be the default. And then by R18, we were to the point that we could actually rely fully on Clang and libc++, so we removed GCC. At this point, all of Android, all of Chrome OS, iOS, all of these are using Clang. So if you are targeting a subset of these operating systems, your code is much more likely to be portable between them. The unified headers I mentioned earlier, this is the gist of what those look like. Instead of having a different copy of this header for every single API level, we have this annotation here introduced in that says that DLVSim was not available until Android 24. The compiler will make sure that you can't actually build against that if your min SDK version is not at least 24. We still have all of the types, the macros, the constants, all the things that you need to use these APIs visible. So if you are running, if your min SDK version is lower than the device you're actually running on, you can still access the new API with DLSim and use all the correct types rather than copy pasting all the types and constants into your project like you would have to with the previous solution. This did unearth a handful of bugs. It was mostly actually old Android workarounds that had been checked in, had to be deleted in order to work with the new option. But deleting code's pretty straightforward, so that's not too bad. libc++, like I said, this was one of the more this was really our main goal, was to give you a up-to-date C++ standard library. Something that actually could support C++ 11 at the time, and then 14, and now even 17. It was a fairly long road to get there. It required those previous fixes first. In R16 was when we really started doing this in earnest. We rewrote that compatibility library with all the bugs, added a whole bunch of tests, made sure that that was nice and solid, and we shipped that in R16, took the beta sticker off, and said, yes, please start using this. It wasn't the default yet. We waited for R17 for that. So R17, it became the default. And then R18, everything was looking good, and we removed the other options. So as of R18, the NDK had a single compiler, the same one we used to build the OS, a single set of headers, the same ones we used to build the OS, and a single C++ library, the same one we used to build the operating system. So it was dogfooding mission accomplished. Does this mean that there's no more disruption when you update your NDK? Unfortunately, not quite. There are still a few changes we are going to need to be making. This is particularly to reduce the size of the NDK. There's a whole bunch of redundant copies of things right now. And if your build system is currently relying on those redundant copies, when I go to delete them, your build system is going to break. Fortunately, as long as you're on NDK R'19 or newer, NDK build and CMake, our two officially supported options, are already onto this. So as long as you're using those, you're already covered. If you do have your own build system, there's fortunately a doc linked down there at the bottom that will tell you all that you need to know to actually integrate this into your own build system. Aside from that, we do have the two build systems still. NDK build is alive and well. It is purpose-built for Android, so often if you are targeting only Android, that is actually going to be your easiest option. That is not the normal case. You are probably also targeting iOS, Windows, handful of other platforms. In that case, CMake is your best bet. It's going to be the easiest option for cross-platform work. And with that, I'm handing off to Elliott for debugging.
Hi. So I think it's not really going to be much of a surprise that the first thing to talk about with C++ debugging is memory issues. So like I said at the start, we're the OS C++ team. So any kind of problem that you guys are having in apps, we've been having in the OS itself for a long time. Typically, we've used ASAN for this. There's a new hardware accelerated ASAN, and hopefully we'll talk about that some other time. But right now, ASAN is kind of the state of the art for this. It's what we're using for the platform. And what we're going to talk about today is how you can use this in the NDK. It is supported in the NDK. It's just perhaps less well known. So these are the kind of issues that ASAN can find. It's basically everything except for leaks. For leaks, we use malloc debug. You can find documentation for that on developerandroid.com as well, in the same place as the ASAN documentations. But the key thing I want to talk about is this wrap.sh. So ASAN on Android is interesting in that the way it works is that you have this LD preload, this shared library that has to get loaded before your code starts. Basically, it intercepts all of the memory allocation and freeing operations. And to do that, it obviously needs to be running before any allocations are actually made. Normally, this wouldn't be a problem, but on Android, when your app starts, you're not actually starting from scratch. You're starting from a clone of the Zygote, which it's generally helpful. It reduces your app startup time greatly, because the kind of common startup that every app would have to do of all the framework stuff has already happened. If you want more details about the Zygote, the art folks are going to be giving a talk tomorrow morning where they'll be talking about some of the new optimizations they've done to that in Q. But for our purposes, all you need to know is this kind of gets in your way for ASAN. So what we added was a thing where if you have a shell script in your APK called wrap.sh and in the correct directory, when we come to launch, when the Zygote comes to launch your app, instead of cloning what's already there, it actually starts completely from scratch. So here's an example of what such a shell script could look like. So $commercial at is basically shell for all the arguments. So what's happening here is when Android calls your wrap.sh, it gives you the exact command line that it would otherwise have run. So here we're just saying, do what you would have done anyway. So the only difference is you're in a completely fresh process. You're not cloned from the zygote. And anything that you output to standard output or standard error will go to the log. It'll go to logcat rather than just being lost like it normally would. Again, because the assumption is you're debugging here, you want to see anything. So here's a slightly more interesting version then. This is saying, so the ASAN options, there's a link a couple of slides ago for all the details about the different ASAN options. This is just an example of like, here are common options that you will want if you're using ASAN on Android. So that puts that into the environment for when your app starts. LD preload, like I said, that's a clue to the dynamic linker. When you start this app, load this library first. And this is kind of the runtime for ASAN. NDK build knows about this. It'll do this magic for you. There's a little wrinkle with Studio at the moment that we need to teach Studio to actually package this. If you're not using Studio, you don't really need to do anything. If you are, definitely go to developerandroid.com. You can see the docs about wrap.sh, and we've got an example there that has sort of screenshots of what you need to do. If you're using NDK build, this is more what it looks like. In your android.mk file, you literally just tell the compiler, please turn on address sanitization. The no omit frame pointer thing is so that we can give you good, quick unwinds. Like I say, if you do this, NDK build picks up on that. It spots that you've said sanitize address, and it'll actually set up the wrap.sh for you. So like I say, lots more documentation on that. It is kind of complicated, but once you get the hang of it, it's not too bad. And there's documentation about that on developerandroid.com that includes a few examples. File bugs if you have trouble with any of that. So another thing we have that we've been using this, again, the platform has used this since 2012. We've used this for a long time now. But by default, NDK users aren't getting this. If you want us to catch easy sort of buffer overrun bugs, if you define fortify source to 2, again, you can look this up on the web for details. You define fortify source, you can actually have us, behind the scenes, the compiler, if it can do so, will prove at compile time that your code is either correct or incorrect. If it's incorrect, it'll just spew out an error, and you can fix it there and then. If it can't prove it, it'll actually insert a call to a slightly different routine that will do some runtime checking. So in this example, this is something obviously very contrived, but this is something that the sort of static analysis built into the compiler doesn't actually spot. It doesn't realize that that 32 is going to be used as that parameter to read. So it turns this into a runtime check, and if that fails, you then get a nice clear abort, and the abort message will be along the lines of, fortify the specific function you called, and then what you asked it to do and what it thinks the current state of the world is. Similar to that, an even easier case, we have a lot of sort of app compat issues where SE Linux policies have changed, or permissions on some file have changed, or even the existence of a file has changed, but apps are assuming, oh, I just open this file and then I read from it, and they kind of plow on without actually checking for errors. So it's simple cases like that where it's never valid to give a null file pointer to any other std.io function. So we will actually just, on recent builds, we'll just blow you out of the water. Nice clean abort, nice clean error message. Another similar thing on more recent builds is that there's been a lot of confusion about pthread-t, which is what you get from pthread create and you use with all the other pthread functions, and pid-t, which is basically just the integer that the kernel uses for its raw thread. And you do sometimes need to deal with both of these depending on what your app is doing. You can get a pid-t from a pthread-t. There's a pthread get-tid np function that you can call. So if you're using some kind of low-level Linux API that requires a tid, you can do that. What you can't do is you can't give a tid, a PID, to one of the pthread functions. Historically, it would just silently do nothing, because it would look on its list of current threads, say, I've not heard of that, that's not a thread, and do nothing. Nowadays, it actually catches this, again, nice clear abort, and tells you what you've done. Usually this means, if it's a low number like this, it means that you've made this pthread and TID confusion. If it's a high number, that means you've lost track of one of your threads. It's basically the thread equivalent of like a double close or an invalid free. Those are often a bit harder to debug. Something brand new in Q that's new to Android is FDSend. So file descriptors, it's what's behind the scenes of like the std.io file or the C++ file APIs. It's an integer. It's what the Linux kernel uses to represent an open file. And it's quite easy to mess up the ownership of these. And what's really unfortunate is that the kernel does a kind of first fit allocation. So if you allocate 5 files and then you close one and open another, you'll get that same number reused. So it's really hard to debug these. So what we've done, we've actually added tracking for this to the C library. The link at the bottom explains how if you've got sort of higher level classes that control some resources that have file descriptors, you can actually take part in this. But we've wired up the basic classes, the basic structs, things like file in std.io, so that this example on the slide, for example, this is a real bug that we actually had in Android that was found by this. Obviously, the real one was spread over multiple files and hundreds of lines, but it boils down to this. That now is a nice clear abort. Well, there's actually 2 modes. Again, see the documentation. You can either, by default at the moment, it just logs if it finds an issue and then lets you carry on. So it preserves that kind of backward buggy behavior. Hopefully in future we'll actually make that fully enforcing, but you can do that yourself in the meantime. So unwinding, this is whenever you have a crash, you've seen the sort of stacks that you get from that. This is behind the scenes, there's a piece of code called the unwinder, which is basically just crawling up your stack, working out what called what. In the past, it worked fine for C and C++, but it kind of fell apart when it hit Java. So one thing we've done more recently, we've written a completely new unwinder, and the major feature of that is that it actually understands Java and Kotlin frames. It doesn't matter whether they're ahead of time compiled, jittered, or interpreted, it'll do the right thing. In Q, we've added a few extra little tricks. Elf build IDs are useful. Every object file, every executable you have has a hash encoded in it. We'll actually show those hashes in Q so that you can, sometimes you're not sure, like, is this really were they running the right version of the code that I think they were running? Am I debugging against the wrong thing? You can check that out. So here's an example of what the stacks used to look like. The blue part's the C++. That used to work fine. But as soon as we'd hit Java, we'd basically stop. Because the way Java, the way the ART runtime maintains its stack is very different. In P and Q, we've actually taught it about that. So this is the kind of stack you'll get these days. It doesn't even matter whether it's interpreted or jittered. We'll just do the right thing. We even have, if you have your own JIT, we actually use the same kind of API behind the scenes that things like GDB use for this. So you can actually tell us about your own JITs as well. What can you do when you have a good unwinder? Profiling is an obvious thing that comes to mind. In NDKR 13, we shipped a thing called SimplePerf. This is basically like the Linux perf tool. It's a command line tool you can use. It's useful, and it was certainly useful for the OS people, not so useful for app developers, because you can't generally run your app whenever you want. One thing that we did as a sort of stopgap was we added a tool to give you sort of HTML flame graphs that you could then see in the browser. But obviously, the real aim was the GUI profiler. Hopefully, you saw that. This was released in Studio 3.1. It was mentioned in the Studio blog post, and hopefully you've tried that. If you haven't, that might actually be worth switching to Studio so you can try that. So this is what the command line looks like. Basically the same. If anyone's familiar with the Linux perf tool, it's basically the same. There's these separate record and report steps. We also support annotation if you actually want to see, right down to the assembler level, where was my code. You can connect to existing processors, but again, the easiest way to do that is just use Studio. The Studio UI is the picture in the foreground. The picture in the background is the sort of HTML thing we have. So now we'll talk about some of the things that people hit either when switching to, from GCC to Clang, or from GNU-STL to libc++, or just in fact in terms of upgrading between different versions of the NDK.
So this was a very common issue we saw when people were updating to the unified headers. You would update, and suddenly your code would no longer compile because some function that really ought to be there was missing. Really common case for this was mmap just disappeared. The reason for this was that Bionic supports this feature called file offset bits. It allows you to specify that you want a 64-bit off-T so you can deal with files larger than 2 gigabytes. This was a feature that wasn't in older NDKs, so if you set file offset bits when you were using an older NDK, nothing happened. It failed silently. You got no indication that nothing happened, and it moved on. When you then upgraded, you were getting this feature, and if you asked for it before it was actually available, your build would fail. Fortunately, the fix for this is extremely easy. If all you want is the old behavior back, grep through your project, find the line that says file offset bits. It'll be in either one of your build scripts or possibly in one of your source files. Just delete that line. Everything will be back to the way it was. If you do need large file support, the answer is a bit more complicated. Essentially, you need to figure out what your MinSDK version is, what you're OK with your MinSDK version being, which subsets of the APIs you need. Fortunately, this is really well documented. The doc link there, you can search in our bug tracker. If you have more questions, just file a bug. We're happy to help.
So I think probably everyone who has native code has seen this. You run your new version of your APK, you get an unsatisfied link error. We had this ourselves in the platform, so we have debugging information in there. Click. If you set this property, you don't need a rooted device for this. Debug properties you can set regardless. You can actually turn on the full logging from the dynamic linker itself. It'll tell you everything, every file it considers, and it'll tell you why it didn't open it. So rather than just kind of the short DL error message that you get in the unsatisfied link error, if you really want to see the full information, you can here. No example of this because it is just far too verbose.
Another common issue you'll run into, particularly while updating to a new compiler or switching between different types of compilers or even just to a new version of the compiler, is undefined behavior. C++ is full of undefined behavior. It's very exciting. This can just lead to all sorts of surprising behaviors in your application. So fortunately, Clang gives you a really good tool to try to sort out these issues. It's undefined behavior sanitizer. Like with ASAN, you can enable this quite simply in your Android.make. If you add these flags, instead of just unpredictable behavior at runtime, you will get a nice stack trace and a crash in logcat that explains what went wrong and where it went wrong. This is also extremely useful for security-conscious code. It is much better to just stop and restart rather than continue into unpredictable behavior for security reasons. We actually ship with this on in the platform for some modules, things like stage fright, for example, back in MEL or M, whenever that was. Undefined behavior sanitizer was the only tool we had that could actually catch that bug. And so we now keep that on as a mitigation.
Right. So one thing that also caused trouble for people who were switching from GCC to Clang is that Clang is a lot fussier about assembler. This example, there are 4 different instructions that might be. It's probably obvious to a human which one that they meant, but Clang refuses to guess. GCC would just guess. The workaround, if you don't have time to work on this right now and you just want to get on with your life, fno integrated AS, that lets you use the binutils assembler behind the scenes, so you'll get the existing behavior. We actually moved forward and fixed all of the ambiguities in our code. The easy trick for doing that is just use objump.
Another common problem, you will go and update your SDK. It will update the NDK with it, and now your build is broken because your Gradle plugin didn't upgrade. There are a handful of assumptions that the Gradle plugin will make about how the NDK is structured. We are doing everything we can to remove those where possible. But fortunately, there's another really easy fix for this problem. Out in beta earlier today with Studio 3.5, you can actually specify your NDK version in your build.gradle right alongside your Gradle plugin version. That way these two things remain in lockstep. You upgrade them at the same time, everything will be fine. Again, that is Gradle 3.5 plugin, so you will need that first, but from then on, you're covered. This also lets you install multiple versions of the NDK easily. So if you're working on multiple projects and you need different versions of the NDK for each one because the project started at different times, that's now nice and easy to do.
So hopefully you already read the blog posts that we've had over the past couple of years about the move to 64-bit and the requirement that everybody supports it. The main thing we want to talk to you about today is just some tips. So we had this problem back in Lollipop. Like my team, we basically spent the entire year fixing all the code, all these 32-bit assumptions. For those of you who are already running the same code on iOS, you shouldn't have a problem. You've already been through this transition. For those of you who aren't, the main thing that caused trouble for us was JNI code. So places where you have a Java class that has some kind of native peer, that was all using JInt for us, so we had to go through and catch all of those. These warnings, and this actually turns these warnings on and then makes them errors. This was completely necessary for us to fix the platform. These catch places where you're converting a 32-bit int to and from a pointer. A trickier one, a less obvious one, is implicit function declarations will hurt you as well, because the old KNR assumption is that if you don't tell the compiler what the type of a function is, the assumption is that it returns int, which means 32 bits, which means it'll truncate your pointer. So in this example, foo actually returns a char star. We didn't tell the compiler that. We ignored its warning about the implicit function declaration, and it said, fine, I'll just drop those top 32 bits. And obviously that doesn't go well at runtime. So that's the thing to add to your build if you actually want the compiler to just say, no, this is wrong, I'm not going to do that. So Dan's now going to talk about some of the things that we're working on for the near future.
Yes, so somewhat short term on the roadmap, we are looking into a new linker. Right now we have BFD and we have gold. We are looking into LLD for the NDK. We are already using LLD for the platform. It, for one, is a lot faster. For something like linking the Linux kernel, it is actually twice as fast. So instead of a 3-minute link step, it is only 1.5 minutes. It is also a lot better at detecting ODR violations and reporting them in useful ways. If you've ever tried to debug one of those with one of the other linkers, it can be quite a pain. It's also got better support for the newer Clang features. LTO will work better with LLD. This is already in the NDK as an experimental feature. It has been for a release or two now. It's still got some rough edges in the NDK, particularly on Windows. It doesn't always work. We are always working on this. I believe R21 will have most of those issues fixed. However, other cases it does work. Like I said, we are using this for the OS, so it does work in a good number of cases. If you are not impacted by any of the existing bugs and you do want your builds to be faster, it is worth a shot. If you do encounter bugs, please file them. This is still quite early for us, which is why there is no solid roadmap here. Normally we would say, you know, we're going to make this the default in this release and then remove it in this release. We haven't made it to that point yet. But please do try it out if you get a chance. A larger task here is making it easier to access third-party libraries in your NDK applications. We want something as simple as just apt install OpenSSL dev. If you've ever tried building that for Android, it is quite a hassle. It does not use any of our supported build systems, so you have to make their build system work with the NDK. It can be a hassle. So we are investigating a number of options to make this easier for you, so you can just specify this in your build.gradle. My app depends on curl, something like that. This is really early for us right now. If you do have any suggestions or there's a use case you think we're not going to consider, there is a bug. It is linked from our NDK GitHub page. Please go leave a comment there. We'd love to hear from you on that. It is definitely not too late for us to change our plans here. So yes, help us help you. Try the OS betas, try the NDK betas. sooner you file bugs, the more likely it is that we won't ship them. It is never fun when you find out that the only thing you can do is work around an existing bug because it is too late to fix it. File bugs at our GitHub bug tracker. Give feedback. Even if you just have a question to ask, it's a good place to start. The worst thing that will happen is I will close your bug with an answer. If you do have questions you want to talk to us about in person, we do have office hours tomorrow morning at 8:30. If you are anything like me and that sounds terrible, we will also be around at 2 in the afternoon. And thank you for your time.